Chapter 2, Electron Configuration and Periodicity. We saw when we studied Bohr theory for monoelectronic system that we consider only the interaction between the electron and the nucleus. In case of helium atom, for example, which is a polyelectronic system composed of two electrons, we have to consider three types of energy. First, the kinetic energy of the electrons moving around the nucleus. Second, the energy of attraction electron-nucleus and electron-nucleus. And third, the energy of repulsion between the two electrons of the helium atom. So Schrödinger equation, based on the calculation of the monoelectronic system, cannot be solved exactly due to the presence of the repulsion between the electrons. And the repulsion, in this case, is called the electron correlation problem and cannot be calculated exactly. So for the polyelectronic system, in order to solve the Schrödinger equation, we do approximation and we treat the electron as if it were moving in a field of charge, that is the net result of the nuclear attraction and the average repulsions of all the other electrons. In other words, we do approximation by neglecting the repulsion between the two electrons and by considering that each electron is moving free. In the previous chapter, we studied that the electron has no definite place. The electron is moving around the nucleus and can take any position. In a certain position, we calculate the probability of presence of these electrons. So now the question, how the electrons are arranged in the atom. The electrons are arranged in the atom according to determined principles. And the chemical property of the element depend on this arrangement and on the energies of these electrons. Suppose in hydrogen atom, which is a system of one electron, and this electron is found at the ground state. So the electron should be in the orbital 1s, which has the lowest energy possible. If this electron will pass to n equals 3, so the possibility is the electron pass to 3s, or the electron pass to one orbital of the 3p. In the 3s, we have one room, so we have one orbital. In the 3p, we have three orbitals, px, py, pz, so the electron can pass to px, or py, or pz. Or the electron can pass to one of the 5 orbitals 3d. So we have several possibilities of transition, but since 3s and 3p and 3d are all vacant, so if the electron pass to 3s or 3p or 3d, this is the same since the energies of the vacant orbital in the n equals 3 are equal. In the polyelectronic system, we have to ask 4 questions. Question 1, have orbitals the same shape and orientation? In other words, if we consider the orbital 1s of hydrogen, which is a system monoelectronic, with 1s of the sodium, which is polyelectronic, do 1s have the same shape in the 2 cases? This is question 1. The question 2, in case of hydrogen, the orbital 2s and the orbital 2p are vacant. So by theory, they have the same value of energy. In case of the polyelectronic system, when 2s is filled and 2p is filled, they would not have the same value of energy. So question 2, have s and p orbitals of the same shell the same energy level in case of the monoelectronic and the polyelectronic system? Question 3, we know that orbital s in the monoelectronic system is the probability of presence of 2 electrons maximum. So how many electrons can occupy an orbital s, for example? Question 4, how electrons are distributed in orbitals? Do they follow the same rules? So we pass to question 1. What is the form and the orientation of orbital? In the case of the polyelectronic system, and due to the repulsions between electrons, the orbitals are slightly deformed with respect to those of the monoelectronic system as hydrogen. So if the orbital s in hydrogen is a pure sphere, the orbital s in case of sodium is a deformed sphere. But by convention, we will suppose that the orbitals in the case of the polyelectronic system and the monoelectronic system have the same shape. Question 2, do the energy levels of the same shell in case of polyelectronic and monoelectronic system are the same? For example, we have to know an important difference between polyelectronic system and the monoelectronic system is that for the monoelectronic system, all orbitals in a given principal quantum level have the same energy. Why? Because these orbitals are vacant. Suppose, consider for example hydrogen, we have 1 electron at the level 1. At the level n equal 2, we have 2s and 2p. And since these 2 orbitals are vacant, they will have the same energy. So we said they are degenerated. In case of the multi-electronic system, if orbital 2s and 2p are filled, they should not have the same energy value. This is the case also of 3s, 3p, and 3d, and 4s and 4p. In the case of the system monoelectronic, suppose we have electron at the orbital 1s, and this electron passed to level 3. In level 3, 3s and 3p, 3d are degenerated. That means they have the same energy level, the same value of energy, since these orbitals are vacant. So when the electron passes from 1s to orbital 3, the atom become unstable, so the electron should return to the initial stable state, so to level 1. What are the probabilities of return in this case? If the electron pass to 3s or 3p or 3d, this is the same case. So when the electron return, we have several probabilities from 3 to 2, from 3 to 1, and from 2 to 1. So we have 3 return, 3 probabilities, and in this case, we will have 3 lines. In the case of the multi-electronic system, suppose the electron in 1s pass to 3d. And in this case, the probabilities are different since the energies of the orbitals 3d, 3p, and 3s are not the same. So what are the probabilities in this case? We have 3d to 4s, 3d to 3p, 3d to 3s, 3d to 2s, 3d to 2p, 3d to 1s. Then 4s, 3p, 4s, 3s, 4s, 2p, 4s, 2s, and 4s, 1s. And we have from 3s to 3p and the other return. So in this case, we will have several possibilities in the case of the multi-electronic system different from the single electron system. And for this reason, the atomic emission spectrum will be very complicated. So the atomic emission spectrum of the polyelectronic atom will contain large number of lines spectra, and this is also the observation when we talk about the defects of Bohr theory. But Bohr told us that his theory is only applied for monoelectronic system. Question 3. What is the occupation of orbitals? Or in other words, how many electrons can fit in or occupy an orbital? In case of the monoelectronic system, we studied that the orbital S is the scanner of the motion of 2 electrons maximum. P is the scan of the motion of 6 electrons, D of 10 electrons, and F of 14 electrons. So this is the same case in the polyelectronic system. S 2 electrons, P 6 electrons, D 10 electrons, and F 14 electrons. The question, why in the polyelectronic system we could not have 2 electrons in collision? So this is the Pauli exclusion principle that states no 2 electrons at the same time in an atom can have the same 4 quantum numbers. We can find 2 electrons of same N, L, ML, but never of the same MS. So if we have 2 electrons in this atom, the first electron has N equal 1, 0, L equals 0, ML equals 0. The second, N1, L0, ML0, but they have different spin. And to remember, that spin is the rotation of the electron around itself. Question number 4. What is the electronic distribution or how the electrons are distributed around the nucleus. We have a vow principle that states electrons fill the lowest energy orbital first. In case of hydrogen, we have one electron. So the electron should be filled in the lowest possible energy. So in level 1, and in level 1, we have 1s. In case of the polyelectronic system, we have several electrons that are filled in level 1, level 2, level 3, and in the same level we know that we have sublevels S, P, D, and F. So what is the order of the orbital energy to be filled? According to the quantum numbers, S, for example, suppose it's 1s, so n equal 1, L equals 0, ML equals 0. So this orbital have a psi 1, 0, 0. We put this psi NLML in the Schrödinger equation that is related to the energy, and we calculated the energy of the orbital 1s. In level 1, we don't have orbital p, so we pass to level 2 where we have orbital p. What are the quantum numbers? N equal 2, L equal 1, ML equal -1, 0, +1. We put the value psi NLML in the expression of Schrödinger equation, and we calculate the energy of the orbital p. By the same way, we calculate the energy of the orbital d and the energy of the orbital f. Suppose we calculated the energies of S, P, D, and F for n equal 4. So this is for S, for P, for D, for F. By Schrödinger equation, we found that the energy of 4s is less than the energy of 4p, less than the energy of 4d, less than the energy of 4f. So the electrons in level 4 are filled first in orbital s. When this orbital is completely filled, so this is the motion of 2 electrons, the other electrons are filled in orbital p, and when we have orbital p completely filled, p6, the electrons are filled in d. When d is completely filled, d10, the electrons are filled in orbital f. Orbitals that are in the same sublevel have the same energy. For example, in 2p, we have 3 types. We have 2px, 2py, and 2pz. These orbitals have the same energy. So the electron can be filled in px, or in py, or in pz. First, the Hund's rule, when we fill orbitals that have the same energy, place 1 electron in each before completing pairs. For example, this is the Hund's rules. Suppose we have 3 orbitals p, and we want to fill 2 electrons. It's not allowed to fill 2 electrons in the same room, px for example, and the 2 other rooms are vacant. So this is wrong according to the calculation of Schrödinger. So what to do? According to Hund's, 1 electron is filled in orbital px, then the second is filled in py, if we have third is filled in PZ, then we continue the cycle to add electrons. So if we have 2 electrons, this is the correct distribution of electrons in orbital. In other words, if you have apartment containing 3 rooms, and this room should be filled by 3 students, the most stable state of the apartment is to put 1 student per 1 room. If we put 3 students in the same room, this will increase the energy of the apartment and will destabilize this apartment. This is the Hund's rule. So the electrons are distributed around the nucleus according to determined concepts. Concept 1 is the Aufbau principle. In the same energy level, the electrons are filled in the suborbital of lower energy. In other words, suppose we have 11 electrons around the nucleus. The electrons should be filled in level 1 first, then in second level, then in the third, then in the fourth. Why? Because for n equal 1, the energy is less than for n equal 2. So the electron should be filled in the lowest energy level. Suppose now the electrons are filled in orbital 3, in n equal 3. In n equal 3, we have several sub-levels, 3s, 3p, 3d. So the electron should be filled in the sub-level of lowest energy. So the electron is filled in 3s, then in 3p, then in 3d. The second principle is the Hund rule. For orbitals of equal energy, fill each orbital with 1 electron before placing 2 electrons in other orbital. If we consider, for example, 2p, as we said, we have px, py, and pz. If I have 2 electrons to be filled into p, I fill 1 electron in the first box and the second electron in the second box. It's not allowed to put 2 electrons in one box and the other boxes are vacant. And the third principle is the Pauli exclusion principle that states it's impossible to find at the same time 2 electrons of the same set quantum numbers n, l, ml, and ms. It's possible to find 2 electrons of same n, l, ml, and ms, of same n, l, and ml, but never of the same ms.